Thank you very much for the introduction. Let me tell you about the mechanics of EDID exchange in NMOS and what it gives us in a practical sense. In the good old baseband world, we have some expectations from video devices when we connect a video source to a video monitor. Expectation number one, video appears on the monitor in the best available format. Um, Two, by default, the source doesn't send video that is out of range for our monitor. I need to try really hard to make it happen. Three, if the laptop acting as a source goes to sleep, the monitor does the same automatically to not consume much power. When the laptop wakes up, the monitor comes up as well. And the last expectation, if I change video or audio settings on the source, the monitor will follow along. From the user's perspective, this logic works automatically thanks to such metadata exchange techniques as EDID and info frames. Let me show you how it works in a nutshell. So, when somebody connects a monitor to a video source, the monitor says, hey, I'm a monitor that supports this very long list of resolution and frame rates. By the way, I prefer 4K 120 Hz the most. Metadata format used for this is called EDID. Then the source receives it, thinks, and starts a video feed saying, here is your 4K 120 Hz video feed. Metadata format for this information is called info frames. This exchange lets the source know what the monitor wants and let the monitor know what the source is transmitting right now. Um, but there are some issues related to EDID. Display devices can have various EDID implementation levels, which sometimes causes incompatibility between a source and the monitor. It may be incomplete listing of monitor capabilities, EDID parsing flows on the source side, etc. As a result, there is always some risk the monitor won't come up after the source gets the new ID EDID. That's what this slide illustrates. When the TV was connected to a laptop, things were going fine. After connecting the TV to the desktop PC, video gone. This kind of issue leads us to having a fallback which lets us tweak EDID if needed. In the baseband world, EDID emulators solve this problem. On this slide, we see one EDID emulator, and uh, it takes responsibility of EDID negotiation, fixing problems in the monitor's EDID if there are, and letting the user introspect to video modes, go into the source if they know which ones they exactly want. So if the user knows better what this desktop PC supports and what this TV is able to consume, they can edit the EDIT came from the TV before passing it through to the source. While the state of the art for solving these problems includes some pretty innovative solutions, there aren't solutions that can be made into a standard for AV over IP market. The significant difference between the baseband world and the IP world is multicast streaming. Uh, when there are multiple monitors, in the case of multicast stream, things get complicated. Here we see one monitor saying it supports 4K 120 Hz and Full HD 60 Hz, and another monitor that says I support only Full HD 60 Hz, and the third monitor says I support VGA. What should the source do in this case? Should it start a VGA video feed, hoping that Full HD compatible monitors handle it? Should it do nothing until all the three monitors will pass the same EDIT to the laptop? Uh, or maybe it should start the Full HD stream since two of three monitors support it. That's the kind of problem which EDIT isn't intended to solve, but anyway, we should handle it somehow in the multicast world. So let's sum up problems we need to tackle in order to tie up the baseband and the IP roles. Problem one is that multicast streaming requires not just passing edit through, but some smart edit management. And problem two, Pro V integrators should have the tools they need to when elegant solutions don't work and tweaking needs to be tried. So how can NMOS help with it? There are two NMOS specifications under development for this purpose. AMWA BCP0501 NMOS EDID to receiver capabilities mapping describes how EDID binary can be expressed through NMOS receiver capabilities. AMWA AS11 NMOS sync metadata processing describes an HTTP API which provides information about physical devices called sinks associated with receivers and allow the user to configure the sending side based on the information we can gather from the receiving side. Let's see how it works. Here you see the setup from left to right. There is a laptop with an HDMI output, HDMI to Ethernet gateway, a network switch, two Ethernet to HDMI gateways, and two monitors. Let's consider their roles in the NMOS terms. The laptop is represented as an NMOS source. Its gateway is a sender. Ethernet to HDMI gateways are NMOS receivers, and the monitors are NMOS sinks. You can also see the legend here. In general, the yellow curved lines mean any network wires, and the black curved lines mean any basement wires. But in this particular example, let them be Ethernet and HDMI cables accordingly. Just for clarity, the whole operation between the gateways, IDS IP and gateways, happen through NMOS APIs. Low-level parts such as EDID and info frames stay behind the gateways. EDIDs belong to the sinks and info frames belong to the laptop, just like in our first example with the source and the monitor connected directly with HDMI. Here, the controller does the first step of making a connection. It gets receiver capabilities from the receivers. In our case, the sinks have EDID, so that the receiver capabilities are generated from these EDIDs. The gateway doesn't just convert EDID to receiver caps directly, since it may have its own restrictions for handling video streams from the network. So they should be taken into account in the receiver capabilities. The most important part of receiver caps on this step is video mode supported by receivers. After the receiver capabilities are inside the controller, it starts handling these receiver caps. Let's assume that these two receiver capability sets are not the same. In most cases, it makes sense to calculate overlap between them to make sure we have a list of video modes supported by both the monitors. The controller also may show this overlap to the user to let them tune the video modes if needed. For instance, controller got receiver capabilities from both the sinks, calculated the overlap and showed them to user, and user knows that his network switch has too low bandwidth to handle 8K video, which is listed in this overlap. In this case, user can delete this mode from the list manually before the next step. Uh, when done, controller converts selected modes into media profiles, which is a set of video modes prepared for sender to let it know what video modes are appropriate. After that, the controller puts prepared media profiles to the sender. Under the hood, the HDMI to Ethernet gateway puts video modes from the media profiles into EDID and sets it to the laptop, acting as a source. This conversion again isn't just straightforward. The HDMI to Ethernet gateway may have its own restrictions, which are added into the result EDID. Then the source reads the EDID and starts transmitting video feed with the info frames applied. After that, everything is ready for the ordinary ISO5 sequence. The controller says to the sender, start transmitting the video feed you have, and says to the receivers, start consume the video feed with these network parameters. Now it's time to show you how this sequence works with real NMOS infrastructure. Magnica and Pebble developed reference implementations in order to test interoperability. So let's watch a video recorded by Christian Ricasano of Pebble, which shows how Pebble controller utilizes IS11 of Magnica nodes. Let me select the best resolution. Okay. Here we see Pebble controller, and we can inspect media profiles of sender. At the start point, it has no media profiles. We see two Magnica senders and four receivers. Two of them are Magnica and two just mockups. Then we want to link Magnica 1 sender with Magnica 1 receiver. And we want to inspect uh, media profiles now. After making a connection, we see 44 media profiles on the sending side. They are made from receiver capabilities of receiver 1 and put to sender. And on the receiving side, we can see receiver capabilities, original ones. Also with the Pebble controller, we can check things connected to Magnica receivers. So here we see manufacturer SAM, it means Samsung monitor, and timing parsed from its EDID file. Then we are trying to connect Magnica 2 receiver. It becomes a part of the same connection, multicast stream. And then we check media profiles of the sender again. And we see 36 media profiles now, because now we didn't just take all the receiver caps from Magnica 1 sender, but calculated overlap of the same video formats between Magnica 1 sender receiver and Magnica 2 receiver. Then we are connecting the mockup with two receiver capabilities. Our goal is to get the narrower overlap to check how sender reacts. We remember that there were two media profiles in Mono 1, and here we see only single media profile. So this is a very narrow overlap between the three receivers. The Mon 2 can't be overlapped with the rest of three receivers. So we see error here. Common media profiles can't be generated for all the four receivers. After disconnecting some of receivers, we see how media profiles return back. With a single receiver, we see 44 media profiles as it was at the start. We also may want to check transport file of this receiver and see that it matches media profiles. So sender follows the policy we passed it. After connecting Mon 1, we can check transfer parameters again and see that they're changed to what Mon 1 and Magnica 1 receivers both support. It demonstrates plug-and-play behavior provided by S11. So the system reacts dynamically on any added or removed receivers. Okay, that's it for this demonstration. Well, thanks to Christian for this. I hope you liked it. Now you see a sequence similar to the one performed during this demonstration. The user here selects senders and receivers, which are implied to be part of a single multicast stream. Then the controller gets receiver caps of the both receivers to calculate the overlap, puts media profiles to sender 1, and starts stream. But this sequence doesn't cover one very important case. We remember that EDID may cause problems on the source side. That means that nobody knows how long after reading EDID, step 4 on the diagram, source actually starts transmitting video. Moreover, there is no guarantee that video comes up at all. This case means the sender isn't ready to stream, so we can't go to step 5 or can on our own risk. Uh, the case of source not coming up after putting media profiles is a particular case of absent source, because in general the user may want to disconnect the source from the gateway in any moment. Now the IS11 group is working on the way to handle this case, and let me show you what this way is. As you remember, IS11 describes an HTTP API. Let me show some parts of it. Uh, Now there is a get media profiles operation which returns an empty array if IS11 is inactive, the last media profiles put if it's active, or out of media profile status if there are media profiles, but the NMOS flow doesn't follow them. It's planned to be changed. Get media profiles may return only empty array or actual media profiles, when the new get status operation will show us if media profiles are if the flow is out of media profiles. This get status returns inactive if media profiles were never put ever, active status if media profiles put and flow follow them, out of media profiles if it doesn't follow, and flow is absent if there are media profiles and flow doesn't exist. It describes its case of absent source. After adding status, there are two ways for the put media profiles operation. It may be a synchronous or asynchronous operation. In the case of the asynchronous operation, the controller puts media profiles to the sender. The node immediately responds that it accepted the request without any guarantee they are applied to, and then the controller polls IS11 status endpoint, waiting until the status becomes ready to stream. The problem here is that it is complicated to define the controller's behavior after putting media profiles. In fact, it's able to do what it wants. But how long should it wait for the status change? What is it allowed to do before the status changes and what is not allowed? Uh, the synchronous approach solves this problem, I believe. It adds a timeout status code to put media profiles operation. In this case, the waiting for source coming up is moved from the controller side to the sender side. So controller shouldn't think about this type of decisions. It just puts media profiles to the sender. Uh, if source comes up before some timeout specified on the sender side, the sender responds, okay, media profiles are finally applied. Source reacted in some way on this update. So you can check the status and decide what you need to do the next. If source didn't come up and timeout is reached, sender just says timeout reached, I'm done, check the source. After any of these responses, the controller and the user know what the result is. If the source is okay with the media profile, so we are ready to start the stream. If not, then the controller may try to put another media profile set or start the stream on our own risk. Maybe a source didn't come up after putting media profiles, but user wants to start the stream to make sure his network part is okay. And then go to source, try to change something in its configuration so that status will be changed and stream will go without necessity to make ISO5 connection one more time. I think that concludes my presentation. Thank you very much.
All right. Thanks, Nikita. We do have one question from the audience. Martin, are you there? Did you want to come on screen? Or you can just unmute and talk.
Yeah, I'm ready to answer the question. Could you?
Yeah, no, I'm just waiting for Martin and see if Martin wanted to ask in person.
Okay.
See what happens. If not, so go ahead, Nikita. Why don't you go ahead and answer? So Martin's question was, why this EDID complications? So I think what he's saying is why is EDID so complex? I think you did a pretty good job of explaining it, but maybe you want to dive into that a little bit more.
Why EDID is so complicated?
Yeah.
EDID came to us from the baseband world, and it is a very old format which describes all the monitor capabilities. It describes manufacturer, different ranges, and also it has sections for listing video timings the monitor supports. So we can't really control what EDID is. And as far as it's widespread in the baseband world, we need to handle it somehow. So as part of this IS11 work, we chose only EDID blocks which matters for us, and designed a solution how to translate these video modes from the EDID language to NMOS language. So it is complicated, maybe in fact, because modern monitors support very long lists of things. They can handle many formats.
Yeah. It seems, it's kind of scary how everything works so transparently in the background, but there's really a lot of interchange going on between the devices and the monitors.
Yep.
So is this protocol capable of handling a monitor wall kind of application?
Yeah, I think it can handle monitor walls. I didn't perform tests with it, but the idea is for having not only receivers, but also introducing sinks. In this case, one receiver can have multiple sinks. So if we have a video wall which has a single Ethernet interface going to the network, and four physical monitors connected to it, and some logic inside this gateway which breaks the image on four parts and shows it, this fact can be reflected using AS11. So using its the user can open its controller and see that this particular receiver has four sinks. See their names, maybe positions on this physical video wall. So I think, yeah, this protocol can handle video walls, and I'm anticipating someone who may want to try it out with AS11.
That makes sense. So what about some of the really huge screens that are out there, or the weird aspect ratios, for virtual sets, or some of the banners that are being put into, football stadiums and things like that? Is that going to be part of EDID, or are those things going to stay pretty much kind of proprietary behind some sort of display adapter?
There is some challenge with very big resolutions. For instance, detailed timing edit block doesn't support resolutions greater than 4095.
Ah,
Uh, it's possible to describe 4K in terms of edit, but it's restricted at the moment. DisplayPort comes with new format. So I believe new HDMI will come with a display ID. It's a next generation of edit type information, and for this case, I think it will be just enough to expand the current specifications. So now we have IS11 for controlling the sender and the BCP for translating EDIT to receiver capabilities. So if display ID will eliminate EDIT at all, we are able to just write BCP for converting display ID blocks into receiver capabilities, and the architecture stays the same.